Okay, so I think we'll jump right in, and what I'll be talking about, a little bit of transition from what we talked about before, we're talking multiplicity, incentives and risks as one tooling oneself. I think I have to get into this title of the book. There we go. So it kind of stuck throughout the meeting. My disclosures, I'm another one of the very consultants here, and of course I'm not going to include any information on any untitled views because I'm a statistician. Okay, multiplicity. Well, first off, in the readings for the course, you'll see that I did put a paper in there. It is from a cancer journal, but I think it's a good description of multiplicities and concerns, and it talks about the complexities of it and gives some possible strategies for considering multiplicities. So there is a paper for you to read later on, and you may find that the author has a similar last name to our company, but it is a really good paper, I think, so I keep putting it in there. The concern with multiplicities, multiple comparisons, they come up when we have numerous statistical tests that are performed. Some of these may be real, may not be real, or may be significant just due to chance alone. And we always talk about this thing called type 1 error, which in very general terms is the probability of making an incorrect conclusion of an effect. So when we have these multiple tests, we probably heard this over and over in your groups, you have multiple outcomes with multiple things you want to look at. Your statisticians are advising you, we need to think about multiplicities, we need to think about all everything anyways. This is something you need to have always in the back of your mind, because the more things you test, the more analyses you make, the more times you take a shot on goal in soccer, the higher chance you have of making a goal or having a significant result. So it's something you just have to be careful of and keep in the back of your mind. So we'll talk about some different examples, some situations, and some strategies. So how much of a concern is this? And the concern really varies based upon your question, the type of your project, the phase of your trial, if we want to talk about the traditional phases. So your research question, the project you will determines how much of this amount of error, this amount of risk that you're willing to take. So if you're in the final step, the final big confirmatory step of a new treatment, you're going to want to have a high level of evidence, you want to change clinical practice, and you're going to want to have more stringent control of type 1 errors. That's why things are so tightly controlled in these phase 3 trials. However, in a lot of your studies right now, these are more exploratory studies, these are early phase studies. You may be looking really, really early at some observational data to generate hypotheses. And maybe here you maybe want less stringent control of type 1 error because you're going to have subsequent studies where you confirm these results, where you're really going to follow up and have something tightly controlled to have a higher level of evidence that there really is an effect of a treatment or there really is a relationship here. So the point I want to make is that your type 1 error level control, it needs to be set in the context of your study question. This is something I preach over and over in any aspect of my collaboration is always think about your question. Your question, think of it in the context of your question. Type 1 error control in the context of your question. What your design is in the context of your question. What your analysis in the context of your question. Always think about what is your question that you're looking at here. And the next step is think about what you're going to do next. If this is the final end-all, be-all, you're going to want strict control. If you're going to have subsequent studies where you're really going to work to confirm this, maybe you're willing to take a little more risk here and have that appropriate context when you report your results. So multiplicities, multiple comparisons, it's a consequence of having lots of data. You've worked very hard through your projects here, you submit your grant application, you get it funded, you want to get your money and your efforts worth. You're going to probably collect a lot of information. And that's perfectly reasonable. It's easy to do with the computing resources. We have the storage space available. We have the databases available. We can collect a lot of data. And we also can process a lot of data. It's very easy to do a lot of analyses quickly, and it's very tempting to just go in and, look at this test here, look at this test here, this with your outcome, look at all these different subsets. It's very easy to do. And it becomes very, very tempting to explore anything and everything to find something significant. But your results need to be credible and they need to be reproducible. You don't just want this to be a one-off kind of conclusion. So we get very tempted of looking for these low p-values and thinking that's what we're looking for, instead of thinking about what is your question and what is leading to this analysis. So let's talk about a bunch of examples. I have a whole bunch of examples, and a lot of them are real-life examples of that experience. I kind of put them into 3 general categories. Multiple tests across multiple treatment arms, a very natural one if you have multiple arms in a study. Multiple tests among subgroups, and this is one you may, or most, I would say is probably most common, and you'll probably have to deal with a lot. And then multiple statistical tests performed while data is accumulating. And Melanie kind of talked about this in her talk. You heard about interim analyses in some of the trials she was talking about with her designs. So the first most natural one, multiple treatment arms. So let's say you have a randomized trial. You have 4 active doses of a new drug, and you've got a comparison and control or placebo arm. And your natural thought is, oh, I want to compare each active drug, active dose to control. And so now I've got 4 tests. I've got these 4 doses. I want to compare each one to the control. But let's say your doses are ordered, and this is completely hypothetical, 1, 2, 3, and 4 milligrams. You've got increasing doses. And so you think, okay, I've got these 4 doses. I have to compare them all to control to see if there's a difference or an effect. And you run the trial, and your p-values in order are 0.2, 0.18, 0.04, and 0.3. And you look at these and you say, oh my gosh, I got a 0.04, it's less than my significance level 0.05, I'm really excited. But hey, is that dose number 3, which is my 3 milligram dose? My tests were saying there's nothing in 1, 2, and 4, but there is something in 3. So you look, so looking at that and think, do I really believe that 3 is the only effective dose? You know, you need to think about this in context of your question. And also, if you reported this, are others going to believe this when they read your paper? Again, stepping back, think about the context of your question in the background. What was your research question going in, and what was the study designed to answer? Well, likely in this case, if you had 4 doses of 1, 2, 3, and 4 milligrams, you were probably thinking, oh, as the dose increases, I may have more of an effect. So I would have thought there would be some sort of relationship across them, and I wouldn't find some sort of random kind of, or some sort of spurious association in the middle. So simply comparing each dose to control wasn't really your question, wasn't really what you were going for here, but it was kind of where your brain first went thinking, oh, I have to compare it to control. The key here is don't blindly live by p-values. P-values are not the end-all, be-all thing. We tend to search and hope for these p-values less than 0.05, but that's really not the situation here when you think about it in the context of the question. So we should think about these issues when you're designing your trial and writing your protocol. So in this case, what would I have done? Well, I would have pre-specified here and thought, okay, I've got these increasing doses and maybe I'm really looking for the best dose. I think there's going to be some sort of relationship as they go across. And I would have thought maybe doing some underlying modeling response curve. Melanie just talked about a whole bunch of modeling. But I also would have thought what was next. If I was looking at 4 doses here, in this situation, I might have been thinking, what are my better doses? Maybe not my best, maybe it's better multiple doses. Then I'm going to take forward to a confirmatory trial. And then is the situation where I'm really looking to compare each that dose strictly to the standard of care control, or maybe 2 doses too. So by just comparing each one of these here, I had a multiplicity. You can tell in my results they didn't really make sense when I tried to think about them, and I didn't really think about looking at this question the best way with this design. So that was a multiplicity of multiple arms. Multiple subgroups. This is one you're probably going to see a lot. It's very tempting. And so there's this comic, and how many people have heard of the website xkcd.com? Okay, this is my comic that I love from this site. I saw a lot of statisticians raising their hand. I like this one for talking about multiple comparisons and subgroups. And so the first panel says, this woman comes in and said, oh, jelly beans cause acne. And the other stick person says, all right, scientists, let's investigate this. Jelly beans cause acne. And they go through and they do their study, do hopefully a randomized trial, and they found no link between jelly beans and acne. The p-value was greater than 0.05. And so the stick figure says, oh, well, that settles it. But the woman says, no, I hear there's only certain colors of the jelly beans that cause acne. And so the other stick figure goes, scientists, let's go investigate further. So you can see I have a lot of panels here, so they start going and look at each individual color of the jelly bean. They start and they look purple, p-value is greater than 0.05. Brown, p-value greater than 0.05. So I've got 10 panels here of 10 different colors, and all the p-values were greater than 0.05. We still haven't found association, but they're not done with all the colors, so they keep going. We've got 10 more panels here. We go through nothing with gray, nothing with tan, nothing with cyan. We get to green. Ooh, look, p-value less than 0.05. And you can see that's that 4th panel on the top and say, whoa, we've got the magic p-value. But they kept going. They wanted to get all the colors done. And if you look through all these panels, you can see that we've had a total of 20 panels, and we found one where a p-value was less than 0.05. But when they were done, the news story is green jelly beans are linked to acne. So what happened here was they started out by saying our jelly beans cause with acne. There was nothing. They went to subgroups, they did 20 different ones, they found only the green one, but what they reported at the end was green jelly beans cause acne. That's not the context of what was studied here. That was a subgroup that went and dug and did p-hacking to do a bunch of different analyses to look for something that had the p-value less than 0.05, and that's the only thing that was reported, so this is not the context of the research that was done. And the readers now think, oh my gosh, green jelly beans cause acne, but if you saw the full story of how this started and what they went through, I'm not sure certain that green jelly beans cause acne. And they don't, because I eat a lot of jelly beans. And I like so I can, well, N of one, but okay, couple more real examples. Real/hypothetical. I kind of changed a few things here. But let's say you have a randomized study and you're comparing intervention A to the standard of care. You know, really, you went in, Rob talked about this Monday night, you're at this light where you really think there's an association here, you get done, you unexpectedly did not find an effect or relationship between the intervention A and the outcome. But you have lots of data, you're like, you know, there's got to be something that's going on here. I really think there's something going on. I want to keep looking, I have a lot of data. You start looking, you look within males and females. Didn't see anything. Well, maybe it was older males greater than age 50, still didn't see anything. Well, maybe it was older males greater than 50 with pre-existing disease X. Aha! I find a relationship with a benefit of the intervention. Now, the key here is, do you believe it with the evidence in this trial? You didn't think this going in, because if you would have thought that in this very distinct subpopulation, you would have had the inclusion-exclusion criteria to enroll men older than 50 with pre-existing disease X. Now, you look at this, and maybe there's a real reason here. Maybe biologically this does make sense. This isn't something where you're just trying to rationalize it. Maybe there does make sense. You really want to publish this result, but you know that you went through and you did a lot of digging and a lot of combining to find this relationship. And you want to publish it, what should you do? How should you frame it in the context of the multiple combinations you examined? And my suggestion was, be honest, state what you did. If you think this is real and this is something that has additional follow-up, you should say, okay, the original study was designed to look at this. I did analyses A, B, and C, and then I came upon this, and this is what I came upon the result, and this is my conclusion. You need to give the full story. And then you would likely need to have a subsequent trial to reproduce that result and show that it is a real effect, because of how you came about it in the beginning. Another example of multiple testing, and this is also one you'll probably run into, and I saw a lot in one of my previous roles. So you have a trial going on, you have half the subjects enrolled, and the data and the outcomes are collected. You didn't plan ahead of time that you were going to have any sort of interim analysis. This was a trial that's going to run beginning to end, and then you're going to get done and analyze the data. But you look at, oh, the abstract deadline for this big meeting is in 2 weeks, but my trial's not going to be done. But when the meeting happens, my trial's going to be done, and I really want the opportunity to present my results, so I want to submit an abstract. So the question is, and I've had this posed to me, is can I analyze the data now and submit an abstract if I see a positive result in the data now, and then when I go to the meeting, I'll just update it and present the information there. So the key here is no, because your trial was not designed to have this interim analysis. That wasn't pre-specified. You weren't planning to do this look ahead of time. You didn't have a pre-specified threshold of what was going to be a significant result. This wasn't part of the plan ahead of time. And you're also stepping into a very dangerous territory. You could do this analysis ahead of time, see something that's going on, say I have an association, have perhaps regression to the mean later, all of a sudden you go to the meeting and I don't have evidence of any sort of association, and now you're really stuck in a bad situation. You're giving a talk or giving a poster that says I have no relationship with my abstracts that I did, and everyone knows that this was something that was not pre-specified, and you didn't say ahead of time. And this is real. I've had this question posed a lot of times. Another one that I've seen. So let's say your outcome is a continuous measure, and the context is hypothetical, but the situation is true. Real story. So you measure a blood level, some sort of lab level, and you want to see if there's a difference in the outcome between good and bad blood levels, whatever this lab level is. Now, you decided you were going to categorize the lab level as good and bad, but you had to figure out what the cut point was. So you would want some sort of cut point that made sense without just looking at the data and picking it. So you start, and you know the lab levels, you have the standard upper limits of normal, lower limits of normal. And so we started and we did the test, and we had that definition, and that's how we categorized it as an effect. We did the analysis, and there wasn't a significant association. The clinician I was working with came back and said, well, that's really not the right cut point. I should have cut pointed this way. Explain to me why. And I was like, all right, I kind of believe this. Let's try this other cut point, and let's see if there's association between this new good implied level. No, there wasn't, but the p-value was closer. We got down to like 0.065 or something like that. Well, the clinician then came back to me a third time and said, no, that wasn't the cut point I should use. I mean, they had seen this trend of lower and lower p-values to the magic threshold, and came back to me and said, I really think the cut point needs to be at this other one. And it was very clear that by doing this cut point, there was a good chance there's going to be a significant result. And so as a statistician, I was posed with being asked to do this test. And so I told the clinician, I said, well, I will do this test for you if you also, when you report it, report the other two tests at the same time as your other cut points. The clinician was not very happy with me, and I may not have worked with her again. But she decided not to do the third test. But the key was we need to have the full story. We couldn't just take this third cut point, which was clearly made up by digging through the data and looking through a significant result. And so the question at the end was, is should you report there's a difference with only the third test, third definition? No, because you had two ahead of time, and you clearly manipulated the definition to get a significant result. Don't blindly live by the p-values. That first test is meaningful. It was based upon upper limits of normal. You had some sort of standard, and that was the result. That was the evidence that your data had. Okay, example 3 of multiple testing. So let's say we have a large double-blind. Yeah.
So if you do like 3 tests, then the third one was significantly not accepted the 5/3. Okay.
If you did an adjustment, there are multiple, we'll talk about that in just a second, there are multiplicity adjustments. Would that be okay? Well, I would say the way you arrived at that result was clearly kind of a data digging kind of thing. So I still think in the context, even if you reported adjusted for multiple tests, you should be very clear that you did the 3 tests and what the 3 tests were, showing that the cut points were kind of manipulated going through there. So if I was reading it, I wouldn't have a lot of faith in the result, because it clearly just of the sequence of how the testing went about. So it gets to the whole thing of pre-specification ahead of time. Again, thinking about what is your question. Okay, third example, this large double-blind randomized clinical trial. It's going to take 3 years to enroll. You've got the 2 arms, an intervention and control, and the outcome is measured at 3 months. And let's say before the end of 3 years, you're thinking, I want to be able to look at the data. Melanie was talking about this in interim analyses, unblinded during the trial, to determine if you can stop early, possibly for success, or maybe do a look to see if it's futile, and you know this ahead of time. So either you know ahead of time that it's overwhelmingly beneficial, you know this before you get to the end, you want the opportunity to stop and report the result, or you know ahead of time that it's a futile trial and there's no sense keeping going and continuing with both subjects. Now, this is acceptable, but there are acceptable methods for how you incorporate the interim analyses. And Melanie's talk with the rare diseases, where she talked about the interim analyses, there was a lot of work done ahead of time, a lot of pre-planning, a lot of specification as far as when those interim analyses would occur, what kind of decisions could happen at those interim analyses. She did a lot of simulation to understand what the type 1 error rate is for studies, and that things were all controlled, specified ahead of time, put in the protocol, and considered. So it wasn't just, oh, now I want to look at the data and see if there's a result. This was all planned ahead of time. That's the key here with the interim analyses and the looking at the data while the trial is ongoing. There's lots of other logistical issues, and that's another talk as far as who gets to know what when, as far as unblinded results. I'm not going to talk about that here, but I just wanted to mention that. But with these type of interim analyses, if you're doing an early look at the data, often an early look at the data to stop a trial early for possible success is going to require a higher level of evidence at this earlier look than the later one. You want to be overwhelmingly sure if it kept going, you didn't have a regression where it was no longer a significant association or relationship between the prevention and the outcome. Okay, so another example. Let's say we have a clinical trial for traumatic brain injury. Looking at experimental treatment versus a standard of care. And for this treatment, you're not sure how fast the treatment needs to be administered. You think sooner is better. Again, this is a made-up example by a statistician, so if you don't like my made-up part, it's a statistician. So you've got 2 intervals where you're thinking you need to give the treatment. You think maybe within 2 hours after the injury is better, but there might possibly be a good benefit 2 to 12 hours after the injury. And again, here we've got these 2 kind of groups, these 2 kind of windows for when we give the treatment. And you want to compare both of these in both of these situations, both these treatment, when they give that treatment, the active treatment to the standard care in both populations. And let's say in this situation you had a type 1 error, you want control at 5%, and we have 2 tests. And this is just, again, I was just asking, we're thinking, okay, we had multiple tests. Well, I know there are methods to account for multiple tests, to control for multiplicity, and thinking, do I have to adjust for multiple tests? Well, probably one of the most common things you've heard for adjusting for multiple tests is the Bonferroni correction, where you take the type 1 error rate and divide it by the number of tests you're going to perform. Now, that's it is very valid, but it's a very, very harsh way to control, because your significance level now has gone from 0.05 down to 0.025. Doesn't mean there's anything wrong with it. It's just very harsh correction, a very harsh consequence of multiple tests. So in this situation, Bonferroni adjustment, like I said, goes down to 0.025. And so now we know that we have a significance level of 0.025. But if we look at that with the original sample size we had, now our power is lower. And so in order to get our power back up to an acceptable level for the study, we have to enroll more subjects. So the consequence of doing these multiple tests here is a larger study. But again, step back, let's think about the question. Would you think that giving the intervention quicker would yield better results? Yes. So if the intervention didn't work in the 0 to 2 hours, would you even want to test the 2 to 12 hours? Does that even make sense? And in this situation, I would say maybe not. So maybe here, instead of this harsh Bonferroni adjustment, there's a different method you can use in this situation to account for the possible multiple tests. And yes, there is one sort of option. You could do the testing of the active versus control in the 0 to 2 hours group first. If it is significant, and only if it is significant, then would you go test in the 2 to 12 hours group. If you don't find anything in the 0 to 2 hours group, you're done. Because finding something in the 2 to 12 hours doesn't make sense anyhow in the context of my biological background in this question. So the key here is this is pre-specified in control in the protocol, pre-specified how you're going to do the testing, pre-specified for the significance levels, the type 1 error control. It preserves the power for the comparison in the 0 to 2 hour group. So we didn't have to increase our sample size. And it also can be shown that it preserves the type 1 error rate. So again, step back to the question. So a bunch of different examples here, and I'll just mention one in situation. You may have seen earlier this year, there was a lot on Twitter about a researcher at an institution with a food group at Cornell, that their research was criticized because there was some inconsistency between papers, and a lot of information came out about possible data dredging, possible key hacking, possible digging into the data, just looking for significant results, and then presenting those results as the end-all be-all of the study. And it was on Twitter a lot earlier this year. There were different news articles about it. And one of the keys that made this, the research suspicious, is they looked across all the different papers that were published from the studies, is they kept seeing sample sizes changing. You know, well, the sample size here was, I don't know what the numbers were, it's 220, but then they reported the same study here, and they only said 179. And they were showing all these different results and associations in these nutrition or these food group studies, but there was lots of inconsistency and differences across the study populations. And there wasn't the context of multiple analyses were done, why these sample sizes were changing, justification for it, and it brought into a lot of questions about the results and whether these things were real. And there was a whole lot of stories about it, and there was different reviews of the scientific conduct. But the key is by what was done, it brought into question the research the results. It brought into question the resulting conclusions that were put forth because the appropriate context wasn't given in all the analysis that were done and how they came about with these research questions. So how would I handle these multiplicities? in a situation like this. The first thing I do is you have to think about your study question. You've been talking about this over and over in your small groups. You think about selecting a primary aim and a primary outcome. If you can have a single goal in your design, that's your main goal. It doesn't mean it's the only thing you're looking at, but the main goal, and that's what you designed your study around, is what you designed to answer. Obviously, you have one question. You don't have to worry as much about multiplicity. Now, that doesn't mean you may not have multiple tasks, multiple arms. You could have multiplicity issues. That's okay. But you need to think about your question and make sure it is possible to have that single goal for the strength of what you can say at the end. That'll make things easier. So if you have a single goal, limit it. But it doesn't mean you can't have other aims or secondary analyses or exploratory analyses. These subjects are participating in your research. They're volunteering for this. There's a lot of information there. There's still things that can be learned, and you don't want to toss that away. You just need to be careful with what you do. These exploratory secondary analyses do not require the same level of evidence. The conclusions made are more exploratory, and you need to say that. So the key with your protocol is the pre-specification. You probably heard this over and over. Statisticians were always asking you what's primary and secondary. We're writing statistical analysis plans. But you need to define this and be very clear in your protocol what's the primary, what's the secondary analysis. And you need to be very clear in your papers, too, what's the primary, what's the secondary analysis. You need to defend how you will handle multiple tests or defend if no adjustments are made. If you're doing a lot of tests and never address the issue of multiplicity, then you're going to get questioned in the results. If you if you address it up front and make very clear how strong these results are. This was my primary analysis, what the study was designed to do, or these were exploratory analyses. I'm drawing my conclusions with care. I'm going to have a follow-up study to confirm the results, designed to look at this. You can put it in the appropriate context. When reporting your results, be clear on how you arrive at the results. What I was saying, this is primary, secondary. How many subgroups did you examine? If you did 20 subgroups looking for the green jelly bean, that paper should have said, we looked at 20 different colors, we found only green, and that should have all been there in the same headline. It shouldn't have just been green jelly beans caused acne. Were the subgroups predefined? No, they did not think about looking at colors of jelly beans, they were just thinking jelly beans in general. Again, it wasn't the appropriate context when the result was reported. Interpret correctly and don't overstate, say what you did. There are adjustment methods. It usually requires a higher level of evidence, a higher probability that you do have association. And there is a consequence for doing this. You may make more type 2 errors where you conclude that there's not an effect, but there was, because you want to have the more multiple tests. So you need to balance these two factors, the desire for multiple tests versus the chance of the consequences of a larger study or making more type 2 errors. But bottom line, it's complicated. There's not one answer. I can't say in every, I give you a general situation. This is what you do. This is the plan. You just need to be clear about what you're going to do, be pre-specified, keep track of everything you analyze, adjust where warranted, but best to focus during the design to limit the possible for multiple tests and multiplicities. You want your results to be reproducible. If they're from exploratory analyses, you may need another study confirmed, and you should state that when you report your results. Consider it carefully in the context of the research question with respect to biologic rationale of previous published studies. Don't just try to rationalize it on your own. Hopefully you have some evidence out there if it was something that came about from multiple tests that this is biologically plausible. And then one of the keys that I think I rarely see, and I used to work in epidemiological research when I was in graduate school, if there are multiple publications from a study, you should be very clear about all the analyses and publications planned. So how many times do you see 8 papers come out of a study and you don't know whether you're seeing the 8th paper? I usually know what the first paper is, but you maybe not know that it's the 8th paper or the 2nd paper. And you can get a better feel for how you should interpret those results and what kind of weight you can put to the evidence you've seen and evidence as a clinician if you're very clear about the number of publications planned. And because Rob started this last night, I had to put a picture of my dogs, and because we're talking about multiplicities, I put both of them on, so I had to. Thanks. Any other questions?
For your example of the 2 treatments where you looked at the 0 to 2 and didn't find a signal. If you did find a signal and you went to analyze the second group, would you do a correction then?
No, because it was a gatekeeping procedure. It was pre-specified. You didn't need to do a correction, but it was pre-specified in the protocol that you would only test that if you saw the significant result in the first one. And then statistically, it can be shown that preserves type 1 error. So it was, without getting into a lot of statistical details, there are methods other than just a strict Bonferroni to handle multiple tests. And that was an example of the gatekeeping procedure. But work with your statistician to make sure it gets used appropriately. Other questions? Who's that?
First of all.
Thank you.
Thank you. So if there are, so if you have two distinct questions you're asking from the same data set, two aims that are completely independent of each other, every once in a while I have someone talking to me about splitting p-values for that.
Sure.
But then I find myself wondering if it's truly distinct, you're asking the questions from completely different kind of angles that should overlap. Is that really a situation where you want to adjust the alpha?
Again, it's complicated. I think a lot of it depends on the nature of your study. If you're asking two specific outcomes in a regulatory trial in phase 3 context, there's likely going to need to be some sort of thinking about the multiple tests. It doesn't have to be a Bonferroni adjustment, it doesn't have to be splitting the alpha, but there needs to be some sort of considerations of the two tests for what you want to be able to say as the end as your main conclusion. There are lots of ways you can think about this and build this in design. There's a lot of independence here. So there's nothing wrong with having the two outcomes, but you need to address it head on as far as whether you use some sort of adjustment, what it is, or whatnot. If it's more of an exploratory analysis, there are people that argue that you should never adjust for multiplicities because you're just learning as you go. And I would say you just need to be careful. I mean, I think pre-specification is the key. I think the context of what you want to be able to say at the end. I think the context of what you're going to do next and how this result is used as far as the totality of the evidence are key there. So a lot of it depends on not a straight answer. Oh boy.
Thanks, Michelle, for that talk. What about tagging on to Pooja's question, what about post-hoc analysis of a study that, again, is looking at a completely different angle as far as you specify in the paper that this post-hoc?
Yeah, exactly. So, I mean, you have all this data. I understand you want to use it to maybe look for ideas for future studies. You're going to want to dig into things. But you should be very clear what you did. Number one, that this was post-hoc, and you had no pre-specified plan to test whatever it is, this relationship, this subgroup, or whatever. You should also be clear as far as how many tests that were done before you got to that. I mean, how easy is it to go through and just do 15 different analyses in this whole set of analyses and then get to that one? You should keep track of how many you do. I mean, that gives the whole context of this is 1 out of 50, or this is 1 out of 5. If it's 1 out of 5, I'm going to put a lot more faith in it than if it was 1 out of 50. So it doesn't mean you can't do post-hoc analyses. You just need to be very clear that they were post-hoc, how many tests you did, and what you're going to do next to make sure that it is a real result and it's reproducible. Roger has a question.
So coming back to Pooja's question, and I just want to illustrate how somewhat schizophrenic the medical research community is. A particular journal, whose name I won't mention, but NEJM sounds familiar, has become very aggressive at requiring correction of p-values for multiplicities for all secondary endpoints. So I think all high-quality journals agree that you should pre-specify all secondary endpoints and list them, and you should report all of them, but now they want you to correct. A different journal, I won't mention, but it sounds like JAMA, takes exactly the opposite approach and says you should not correct the multiplicities for secondary endpoints because the top-line result of the trial is given by the analysis of the primary endpoint, and that's what defines whether it's a positive or negative trial, and therefore that provides a gatekeeping protection for type 1 error in reporting secondary endpoints. So the point here is that even in two relatively well-known but now anonymous journals, you're going to get completely different approaches. I don't have a solution for that. It's just a fact.
So again, be clear what you did. Be clear whether it's primary, secondary, and then you may have different opinions on.
And there's another journal that
Yeah.
I won't name, but
in Sandals and emergency medicine, where if you use any p-values for anything other than a primary analysis, we will tell you to take them out, like the p-values.
Oh, well, I have a comment on that. If you're doing general descriptives and you do p-values for all your descriptives and describing your patient population, most often, I think those are unnecessary. Don't test just to test. If you're describing your patient population, your demographics, it's perfectly valid to say I had 40% people that were in the older population and 60% the younger. That's what your goal is. You're just trying to describe it. I don't really care that it's significant difference between the two. I want to know what your population was going in. So again, think about the purpose of what you're trying to do in all of your presentations today. Because I get that in DSMB reports. My pet peeve is in DSMB reports where every single comparison between arms has a p-value with it when it's completely not meaningful in the context of what the DSMB is trying to achieve. So think about the question and purpose.